In the darkness between galaxies, the laws of physics begin to bend in ways we still struggle to explain. There are places where time slows to a crawl, where stars drift alone for billions of years, and where entire galaxies vanish into regions we can barely detect. Scientists now believe most of the universe is made of things we cannot see and forces we do not yet understand. The deeper we look, the more the universe seems to challenge everything we thought we understood. Join us as we unravel the quiet, unsettling mysteries hidden in the fabric of the cosmos. Silent universe. The silent universe begins as a vast expanse where sound itself has no medium, a place so thoroughly emptied of air and pressure that even the most violent cosmic events unfold in absolute quiet. Far from the warmth of familiar atmospheres, silence becomes not merely an absence of noise, but a defining physical condition, the result of a vacuum so complete that waves of pressure cannot travel at all. This silence stretches across interstellar space, where distances between stars resemble deserts of unimaginable scale, and where each fragment of matter drifts through an ocean of almost nothing. Yet the quiet here is not a gentle one. It is a stillness, shaped by forces powerful enough to sculpt galaxies and bury entire suns beneath their influence. Far beyond the faint glow of the Milky Way's crowded regions, silence deepens into a near-perfect state as density drops to mere atoms per cubic meter. These isolated atoms, often hydrogen left from the early universe, drift slowly through gravitational tides that take millions of years to reshape. The early attempts to measure this silence date back to the mid-20th century, when radio astronomers discovered that most of space emits only a faint background hum. The cosmic microwave background, a fossil of the Big Bang released 380,000 years after the universe formed. This relic radiation, mapped in remarkable detail by missions such as COBE in 1989 and Planck in 2009, revealed a cosmos that has spent nearly all its history settling into quiet equilibrium. Yet hidden within this calm are regions where the silence carries enormous tension. Dense nebulae, for instance, store vast quantities of gas and dust in cold, slow-moving clouds, their interiors shielded from external starlight. Sound could travel here, but at speeds far lower than on Earth, perhaps a few hundred meters per second depending on density. Even so, the surrounding vacuum absorbs these potential vibrations, keeping the cosmic landscape essentially mute. One could stand near a forming star, watching jets of plasma erupt across billions of kilometers, and still hear nothing at all. This difference between what we see and what we would hear makes the universe feel strangely detached, as though it prefers observation to participation. Beyond the nebulae lie the immense voids, enormous cavities, where galaxies are separated by tens of millions of light years. These structures were first recognized through galaxy surveys in the 1970 seconds, revealing that the cosmos is arranged like a web, clusters and filaments surrounding deep, empty basins. Inside these voids, silence becomes a structural feature. Gravity works slowly here, tugging gently on stray particles that have not yet settled into larger systems. Without interactions, without starlight, without the agitation of dense matter, these regions remain some of the quietest environments in existence. Yet quieter still is the intergalactic medium, where temperatures climb not because of local agitation, but because energetic photons from distant galaxies ionize the thin plasma. These warmed particles remain too sparse to transmit anything resembling sound, drifting through a realm shaped predominantly by dark matter, an invisible framework whose gravitational influence was established through studies of galaxy rotation in the 970 seconds by Vera Rubin and others. In these regions, silence becomes a consequence of structure itself, a byproduct of the universe's large-scale design. Even black holes, with their violent accretion disks and relativistic jets, uphold the quiet. Though the disk may reach millions of degrees, spiraling inward with furious acceleration, the environment around it is still too empty for sound waves to propagate. The curvature of space-time absorbs nearly everything except light, creating a theatre of motion performed in perfect stillness. The silence here is absolute, not because nothing happens, but because the medium required for sound does not exist. In this vast and intricate cosmos, silence is not the absence of events, but the condition under which they occur. From star formation to galactic collisions, from the glow of background radiation to the slow drift of hydrogen clouds, everything unfolds in a universe where sound has no role. The silent universe is, in truth, an active one, filled with movement, energy, and transformation, yet carried out in a hush that spans billions of light years. As gravitational forces sculpt the quiet regions of space, another aspect of the cosmos takes hold in the drifting distances between stars, where temperature falls away and the warmth of radiation grows thin, revealing the domain known as cold darkness. Cold darkness. Cold darkness settles across the universe in regions where starlight grows faint, temperatures fall toward absolute zero, and the warmth produced by nuclear fusion no longer reaches. This harsh environment is most visible in the vast interstellar spaces that separate stars, where the average temperature sits near 2.7 Kelvin, just a few degrees above the point at which all molecular motion would theoretically cease. This measurement, determined through studies of the cosmic microwave background beginning in the 1960 seconds, reveals a universe that has cooled steadily for more than 13 billion years, expanding and thinning until heat itself became scarce. Far from energetic stars, radiation weakens to a soft, ancient glow left over from the Big Bang. This background forms a thermal floor beneath which nothing can fall, yet much of the universe hovers just above it. Hydrogen clouds drift through this cold landscape, their atoms moving slowly enough that collisions become rare and chemistry stalls into a kind of suspended animation. Within dense molecular clouds, where starlight cannot penetrate, temperatures can fall even lower, approaching 10 Kelvin. These frigid pockets allow matter to cling together, their low temperatures enabling the slow gravitational collapse that precedes star formation. Moving deeper into these regions, the cold reveals an unsettling truth. Most planets, moons, and asteroids spend the entirety of their existence far from life-sustaining warmth. Rogue planets, first theorized in the late 20th century and later confirmed through gravitational microlensing surveys, drift alone through space without a parent star. Their surfaces may reach temperatures hundreds of degrees below freezing, and any atmosphere they possess collapses into ice or vaporizes entirely. These worlds are common. Hundreds of billions may wander the Milky Way, frozen and silent, lit only by the faint glow of distant stars. Yet perhaps the most striking example of cold darkness lies within the Oort cloud, the distant reservoir of icy bodies surrounding our solar system. Extending up to a light year from the sun's influence, this region is so cold that water, ammonia, and methane remain frozen solid for billions of years. Temperatures here likely stay near 3 Kelvin, shaped only by the dim touch of background radiation. The objects in this cloud are remnants from the solar system's formation, preserved in deep freeze since long before life emerged on Earth. Their existence reminds us that warmth is an exception, not a rule. Cold dominates nearly everything. The deeper one travels into intergalactic space, the more profound the cold becomes. Heat struggles to propagate in a universe with so little matter, and photons drift unhindered for millions of years. Even starlight from entire galaxies loses intensity across enormous distances. This creates regions where temperature remains effectively uniform, another sign of the cosmos's vast scale. In such environments, physics behaves differently. Chemical reactions slow drastically. Atomic vibrations weaken. Gases condense into molecular structures faintly held together by gravity and quantum interactions. Cold shapes the life cycle of matter, guiding how clouds collapse, how stars ignite, and how remnants fade. Cold darkness, then, is not emptiness, but a form of cosmic governance. It regulates energy, controls the pace of creation, and determines the environments in which matter can evolve. Through its presence, the universe reveals that most of its volume lies far from heat, leaving only isolated islands of warmth in a sea of near-frozen space. As the temperature drops and the light thins across these distant expanses, structures hidden within the cold begin to awaken, leading toward regions where gravity gathers matter into dense pockets and the early stages of star formation begin to take shape. Black holes. A quiet distortion in the fabric of space can grow into something extraordinary when gravity folds inward so sharply that escape is no longer possible, giving rise to what we call black holes regions, where not even light can find its way out. The earliest theoretical foundations came from Karl Schwarzschild in 1916, who solved Einstein's field equations and revealed how mass could warp space-time into a geometry so steep that outward escape became impossible. Later work by Oppenheimer and Snyder in 1939 extended this understanding, showing how massive stars collapsing under their own weight could naturally produce such objects. These ideas remained largely mathematical curiosities until the late 20th century, when observations of compact X-ray sources and the precise motions of stars near the center of the Milky Way confirmed that truly extreme gravitational wells existed in nature. In these environments, gravity no longer behaves as a gentle force that keeps planets in orbit. Instead, it carves deep funnels into space-time, pulling matter inward with increasing speed. Gas, drawn toward a black hole, forms an accretion disk, an orbiting structure heated to extraordinary temperatures by friction and compression. The brightest examples, such as those found in active galactic nuclei, can outshine entire galaxies. Observations made with X-ray telescopes in the late 20th century revealed disks around objects no larger than a city, yet possessing masses several times that of the Sunday. These compact remnants are known as stellar mass black holes, the result of stars collapsing after exhausting their nuclear fuel. Beyond these lie supermassive black holes, millions or billions of times the Sun's mass, residing at the centers of galaxies. The one at the core of the Milky Way, Sagittarius A*, was confirmed through decades of precise measurements using infrared telescopes that tracked the orbits of nearby stars. Their paths curve sharply, completing loops in just a few decades and revealing that the central object must be extraordinarily dense. By 2020, the Event Horizon Telescope produced the first direct image of a black hole's shadow, an asymmetric ring marking the edge of the event horizon in the galaxy M87, demonstrating the structure predicted by general relativity. Closer to the event horizon, physics takes on unfamiliar forms. Time passes more slowly near a massive gravitational field, an effect measured through experiments on Earth and predicted by relativity over a century ago. Near a black hole, this slowing becomes extreme. An observer far away would see matter drifting toward the event horizon and appearing to freeze, its light stretched into deep red wavelengths. Yet, From the viewpoint of the falling material, the descent continues unhindered, crossing the boundary without noticing anything unusual. This contrast between perspectives illustrates the peculiar nature of space-time around such objects, where geometry dictates experience. Inside the event horizon, classical physics can no longer describe the behavior of matter. The equations predict a singularity, a point where density becomes infinite and space-time curvature becomes undefined. Whether such a singularity truly exists remains unknown, as quantum gravity, the missing link between general relativity and quantum mechanics, has not yet been discovered. What is clear is that the black hole interior is cut off from the outside universe, sealed behind a boundary from which no information can escape. Although black holes often appear as destructive entities, they also play a role in shaping galaxies. Jets launched from their accretion disks can extend for thousands of light years, distributing energy and influencing star formation in their host systems. These jets arise from magnetic fields twisting within the swirling plasma, converting rotational energy into beams of particles moving near the speed of light. Black holes, then, are not empty gaps, but complex structures where gravity, radiation, and high-energy physics meet in one of the universe's most extreme environments. They trace the life cycles of massive stars, anchor the centers of galaxies, and reveal the curvature of space-time with remarkable clarity. As their influence reaches outward into the surrounding cosmos, another phenomenon emerges in the behavior of matter near their boundaries, carrying us into the strange experience of descent through regions where gravitational pull grows endlessly stronger. Lonely planets. Lonely planets occupy the vast stretches of space where gravity has left worlds without a parent star, sending them into the galaxy as solitary wanderers. These objects, often called rogue planets, were first theorized in the 20th century and confirmed observationally through gravitational microlensing studies in the early 2000s. Instead of orbiting a star, they drift freely, following paths shaped solely by encounters with passing objects and the gravitational pull of the Milky Way itself. Their surfaces exist in perpetual night. With no stellar light to warm them, their temperatures drop to extremes, sometimes reaching hundreds of degrees below freezing. Most rogue planets likely began life within ordinary planetary systems. During the early years of formation, gravitational interactions between young planets can become chaotic. A large planet migrating inward, for example, can destabilize the orbits of smaller bodies. A close pass between two giants may push one outward until it reaches escape velocity, leaving the system entirely. Simulations conducted from the late 20th century onward show that such ejections are common and may account for a large fraction of the Milky Way's planetary population. Even Jupiter-sized worlds can be cast into interstellar space if the configuration of their birth system becomes unstable. Once freed, a lonely planet enters an environment vastly different from the structured paths of a solar system. It moves through regions where starlight is faint and matter is scarce. Without continuous energy input from a star, its atmosphere, if it has one, may condense into ice or escape entirely. Yet some larger rogue planets retain internal heat generated from radioactive decay or leftover thermal energy from their formation. This can keep subsurface oceans liquid for billions of years, much like the hidden seas suspected beneath the ice shells of Europa or Enceladus moons, whose heat sources are well studied through work conducted by missions such as Galileo and Cassini. Detection of these planets remains difficult because they emit almost no light. Microlensing, however, makes them briefly visible. When a rogue planet passes in front of a distant star, its gravity bends the background starlight, producing a temporary brightening. Events of this kind have revealed planets ranging from Earth-sized bodies to objects several times larger than Jupiter, wandering without any stellar companion. Statistical models from such surveys suggest that the Milky Way may contain billions of these solitary worlds drifting silently between stars. Despite their isolation, lonely planets play a role in shaping the galactic environment. Their gravitational fields can subtly deflect particles and smaller objects as they travel, contributing to the slow evolution of interstellar matter. If they pass near a star, they can gravitationally perturb existing planetary systems. The chances are low on human timescales, but increase dramatically across billions of years. Their presence adds a quiet unpredictability to the galaxy's long history. For all their darkness, these planets remain worlds, with structure, mountains, oceans, and atmospheres shaped by the same geological and chemical processes found on more familiar planets. Yet their landscapes lie unlit and unseen, their horizons defined not by sunrise but by the faint glow of distant stars scattered across the sky. The concept of a world adrift highlights how fragile the gravitational arrangements of planetary systems can be, and how many outcomes the universe allows beyond the familiar pattern of orbiting a single star. With these solitary wanderers drifting through the galactic shadows, the wider environment grows more complex, carrying us toward regions where even light itself falters, and the cosmic landscape becomes shaped by objects far stranger and more extreme. Star birth. Star birth begins in regions where gravity gathers cold gas into quiet, heavy folds, drawing vast clouds into structures dense enough to collapse under their own weight. These clouds, known as molecular clouds, drift for millions of years before a subtle disturbance pushes them beyond stability. A passing shock wave from a supernova, the slow tidal pull of nearby stars, or simple internal turbulence can be enough to start the fall inward. Once collapse begins, the cloud fragments into smaller pockets called clumps, each one a potential birthplace for a star. The material within these clumps cools efficiently, allowing gravity to tighten its grip. With the temperature dropping and density rising, hydrogen molecules begin to form stronger bonds, helping the cloud shed heat and continue contracting. At the center of one of these collapsing pockets, a small sphere of gas becomes denser than its surroundings. This embryonic object is called a protostar. It forms in layers, like a slow-moving whirlpool of gas drawn inward from all sides. As it accretes material, its core grows hotter, compressing under the increasing pressure. Temperatures rise from just a few tens of Kelvin to thousands, then hundreds of thousands. In the 1,940 seconds, the work of physicists such as Subramanian Chandrasekhar and later theorists clarified how gravity, temperature, and quantum physics interact during this early stage. Their efforts helped establish the conditions under which nuclear fusion can ignite, transforming a protostar into a true star. Yet before that ignition, the protostar is wrapped in a disk of gas and dust. This disk rotates, flattening under centrifugal forces, feeding the central core while also giving rise to early planetary material. The protostar itself emits fierce, narrow jets, bipolar outflows that carve channels through the surrounding cloud. These jets were first observed in detail during the late 20th century, using radio telescopes that could detect the dense knots within Herbig-Haro objects. They reveal the delicate balance between accretion and expulsion, a process that stops the star from gaining too much mass too quickly. As contraction continues, the core temperature approaches the threshold at which hydrogen nuclei can fuse into helium around 10 million Kelvin. When this moment arrives, the protostar stabilizes. Energy from fusion pushes outward, counteracting the inward pull of gravity. A new equilibrium forms, described by Arthur Eddington's work in the 1920 seconds, showing how radiation pressure supports a star's structure. This marks the beginning of the main sequence stage, the long and steady period during which most stars spend the majority of their lives. The environment around the newborn star remains active. Radiation clears away the remnants of the parent cloud, sculpting it into bright regions such as the Orion Nebula, first catalogued in the 17th century and later studied in detail to understand the mechanics of stellar nurseries. Ionized gas glows in vivid colours, shaped by ultraviolet light. Dust grains warm gently, tracing the contours of shock fronts and cavities. The star, now stable, burns quietly in a state determined by its mass. Smaller stars fuse hydrogen slowly, lasting tens of billions of years. Massive stars burn through their fuel quickly, living fast, short lives before exploding as supernovae. Star birth, then, is the slow transformation of cold matter into radiant energy. It is a process guided by gravity, cooled by molecular interactions, and ultimately driven by nuclear physics. Each new star carries with it the history of the cloud from which it formed, inheriting its motion, composition, and structure. The light it produces spreads outward for thousands of light years, illuminating the surrounding gas and marking its presence on the grand stage of the Milky Way. These young stars settle into their long, main sequence lives. The space between them becomes home to worlds of all kinds, including those that never find the warmth of a parent star, drifting ever further into the dim corridors of the galaxy, where solitary planets move through the deep dark, falling forever. A slow drift toward a region of warped space-time reveals a peculiar phenomenon where descent seems to stretch endlessly outward, defining what physicists describe as falling forever near the edge of a black hole. This effect arises from gravitational time dilation, a key prediction of general relativity first mathematically formalized by Einstein in 1915 and later confirmed through experiments comparing clocks at different altitudes. The deeper an object moves into a gravitational well, the slower time passes relative to an outside viewpoint. As a result, an object falling toward a black hole seems to drift more and more slowly, its signals redshifting into longer wavelengths until they fade entirely. The fall appears to freeze just above the event horizon, giving the impression of perpetual descent. Yet this halted appearance is only a matter of perspective. For the falling object itself, the journey continues smoothly, crossing the event horizon within a finite time. If the black hole is small, tidal forces near the horizon become extreme. These forces stretch matter along the direction of gravity while compressing it from the sides, a process informally known as spaghettification. The mathematics behind this behavior was clarified in the latter half of the 20th century through detailed analyses of curvature tensors, showing why tidal gradients become steeper near compact objects. Stellar mass black holes exhibit such gradients strongly, while supermassive black holes spread them over larger distances, making the fall less violent, at least initially. The experience of falling can be described in terms of geodesics, the natural paths that objects follow in curved spacetime. These paths bend inward near a black hole, shaping how matter, light, and even time evolve during descent. Photons approaching the horizon follow curved trajectories that can loop repeatedly before escaping, producing the luminous rings captured by the Event Horizon Telescope. Matter falling inward releases energy as it accelerates, heating the accretion disk and generating highly variable radiation patterns that have been observed in X-ray binaries since the 1970 seconds. For distant observers, the reason the fall appears endless is that clocks near the horizon run increasingly slowly. A signal sent outward from the falling object must climb against the gravitational field, losing energy and stretching in wavelength. Eventually, the light becomes so redshifted that it moves beyond detectable ranges. To outside observers, the object never quite crosses the event horizon. It simply fades into darkness. This perspective was illustrated clearly in early relativity texts and remains one of the most accessible demonstrations of gravitational time effects. Inside the horizon, all paths lead inward. Even light cannot maintain an outward direction because the geometry of space-time is tilted so steeply that motion toward the center becomes inevitable. The singularity predicted by classical relativity marks the ultimate end of these paths, though its true nature remains one of the outstanding questions in theoretical physics. Efforts to reconcile quantum mechanics with gravity, an endeavor pursued by researchers since the mid-23rd century, aim to describe what happens in this region, but a complete solution has yet to be achieved. Despite the strange physics, the concept of falling forever highlights how relativity blends geometry with observation. Different viewpoints yield different descriptions of the same event, yet both are consistent within the theory. What appears frozen and eternal from one vantage point becomes swift and direct from another. As these gravitational effects shape the behavior of matter and time near compact objects, the wider cosmic environment reveals further examples of extreme processes stretching from collapsed stars to the larger structures that bind galaxies into evolving patterns across the universe. Dead stars. A fading glow in the darkness marks the quiet aftermath of stellar life, where the universe leaves behind remnants known as dead stars, objects that have spent their fuel and collapsed into their final forms. These remnants appear in several distinct varieties, each shaped by the mass of the original star and the physics governing its internal pressure. The study of stellar remnants took shape during the early 20th century, when Subrahmanyan Chandrasekhar's calculations revealed that stars below a certain mass threshold settle into white dwarfs, while heavier ones meet more dramatic endings. His work on electron degeneracy pressure, completed in 1930, showed how quantum mechanics resists further collapse, stabilizing these compact objects even without fusion. White dwarfs, the mildest of these remnants, are roughly Earth-sized, yet contain masses comparable to the Sunday. They no longer produce energy through nuclear fusion. Instead, they shine through residual heat, slowly cooling over billions of years. The first white dwarf to be recognized, Sirius B, was identified in 1862 and later analyzed spectroscopically in the early 20th century, confirming its unusually high density. Its internal structure is supported by electrons packed so closely that quantum rules prevent them from being compressed further. Over immense timescales, a white dwarf's faint glow dwindles until it becomes a black dwarf, a theoretical state not yet observed, as the universe is not old enough for such objects to have formed. More massive stars meet a different fate. When these stars exhaust the nuclear fuel in their cores, they undergo catastrophic collapse, triggering supernova explosions. The remaining core may stabilize as a neutron star, supported by neutron degeneracy pressure rather than electrons. These objects were first confirmed in 1967 when Jocelyn Bell Burnell detected pulsars, rapidly rotating neutron stars, emitting beams of radio waves with remarkable regularity. A typical neutron star compresses more than the Sun's mass into a sphere about 20 kilometers across, forming a crust of atomic nuclei surrounding a fluid of neutrons arranged in exotic quantum states. Their magnetic fields, trillions of times stronger than Earth's, produce high-energy emissions observable across electromagnetic wavelengths. A subset of neutron stars shows even more extreme behavior. Magnetars, discovered through bursts of gamma rays in the late 20th century, possess magnetic fields so intense that they can distort atomic structures. Their surfaces crack under magnetic stress, releasing bursts of energy detectable across galaxies. These phenomena highlight how diverse the afterlives of stars can be, governed by precisely how much mass remains after a star detonates. For stars exceeding roughly 3 times the mass of the Sun, even neutron pressure cannot halt collapse. Their cores contract into black holes regions already explored earlier, where gravity overwhelms all known forms of matter. Such transitions from neutron star to black hole are rare, but have been suggested by observations of unusually heavy neutron stars approaching theoretical limits. Dead stars also contribute materially to the galaxy. Supernova remnants distribute heavy elements, iron, gold, oxygen, into surrounding space, enriching the interstellar medium. Observations of remnants such as Cassiopeia A show filaments of shocked gas expanding outward, while X-ray mapping reveals the distribution of freshly forged elements. These materials later become incorporated into new stars and planets, linking the deaths of previous generations to the origins of later ones. Though silent, these remnants continue to exert influence across millions of years. Their gravitational fields shape nearby stellar systems, their cooling light offers clues about stellar evolution, and their explosions trigger new cycles of formation. Dead stars are not mere endpoints, they are active participants in the galaxy's long story, carrying the marks of the processes that created them. Remnants drift through the Milky Way. They become part of the larger structures that populate galactic space, drawing our attention toward the immense, powerful systems that dominate the cosmic landscape on much greater scales. Galactic monsters. In the vast stretches between stars, colossal structures loom across hundreds of thousands of light years, earning the informal title galactic monsters for the sheer scale and energy they command. These giants come in several forms: spiral galaxies, elliptical galaxies, quasars, and active galactic nuclei, each one containing billions of stars and powered by processes far more energetic than anything found in individual stellar systems. Their study accelerated during the early 20th century, particularly after Edwin Hubble's work in the 1920 seconds, demonstrated that these systems lie far beyond the Milky Way, expanding the known universe dramatically. Spiral galaxies, such as the Milky Way and Andromeda, appear graceful when viewed from afar, with arms sweeping outward in luminous arcs. Yet beneath this elegance lies turbulent motion. Stars orbit the galactic center at speeds reaching hundreds of kilometers per second, guided by gravitational fields shaped not only by visible matter, but also by dark matter, a form of mass inferred from galaxy rotation measurements carried out by Vera Rubin in the 1970 seconds. Without dark matter, the outer regions of galaxies would rotate far more slowly than observed. Instead, they move as though embedded in invisible halos, extending well beyond the luminous boundaries. Elliptical galaxies form another category of galactic monsters. These immense, rounded structures often contain older stars and far less gas than spirals. They likely result from mergers events in which two galaxies collide and combine. Observations and simulations since the mid-20th century have shown how such interactions scramble stellar orbits, creating the smooth, featureless shapes typical of ellipticals. Some grow to extraordinary sizes, becoming central dominant galaxies within galaxy clusters. Their masses can exceed 100 trillion suns, forming some of the largest gravitationally bound objects in the universe. Still more dramatic are quasars, and active galactic nuclei. These objects shine with luminosities rivaling entire galaxies, despite being powered by regions no larger than a star system. Their central engines are supermassive black holes, accreting vast amounts of gas. The bright emissions were first identified in the 1,950 seconds and 1,960 seconds, and subsequent studies revealed redshifts so large that quasars must reside billions of light-years away. The energy produced arises from gravitational infall, where matter heats to millions of degrees before crossing the event horizon. Jets of charged particles can extend for thousands of light-years, visible in radio, optical, and X-ray wavelengths. Galaxy clusters add yet another layer to the landscape of cosmic giants. These structures contain hundreds or thousands of galaxies bound together by gravity, along with hot intracluster gas that emits strongly in X-rays. Observations by missions such as Rosat and Chandra have mapped this gas in detail, revealing temperatures of tens of millions of degrees. The dynamics of clusters also provide some of the earliest evidence for dark matter, following Fritz Zwicky's measurements of galaxy velocities in the Coma cluster in 1933. Despite their size, galactic monsters are shaped by delicate balances. Gravity draws material inward, while radiation, magnetic fields, and dark matter determine how structures stabilize and evolve. Interactions between galaxies, tidal forces, collisions, and mergers continuously reshape the cosmic landscape. Over billions of years, spirals may transform into ellipticals, clusters may accrete new members, and active nuclei may switch on or shut down depending on their available fuel. Through these immense systems, the universe displays its largest architectural patterns. They reveal how matter organizes itself across scales so vast that human reference points become almost meaningless. Yet their study has given astronomers insight into the life cycles of galaxies, the behavior of dark matter, and the evolution of cosmic structure from the earliest epochs to the present day. These enormous formations exert their influence across intergalactic distances. Their gravitational reach draws us onward toward even deeper aspects of the universe, regions where density changes, motion slows, and the cosmic web reveals the quieter, colder realms lying between its luminous threads, cosmic storms. Flashes of high-energy light, sweeping across distant regions of space, reveal the presence of cosmic storms, events where the universe concentrates immense power into moments that reshape entire environments. These storms take many forms, from gamma-ray bursts to supernova shock fronts, each one driven by extreme processes occurring in the hearts of massive stars or within the energetic surroundings of compact objects. Gamma-ray bursts, first detected accidentally in the late 1960 seconds by military satellites designed to monitor nuclear tests, remain among the brightest explosions ever recorded. Lasting from milliseconds to a few minutes, they arise when a collapsing massive star or merging neutron stars channel energy into focused beams traveling at nearly the speed of light. Yet hidden within quieter corners of the cosmos, other storms unfold on scales that stretch across light years. Supernova remnants expand outward as ripples of gas and dust accelerated by the blast of a dying star. Observations of remnants, like the Crab Nebula, whose explosion was recorded in 1054 CE, show filaments of charged particles spiraling along magnetic fields, creating X-rays and radio waves detectable long after the initial flash has faded. These expanding shells compress the interstellar medium, triggering new waves of star formation and distributing heavy elements crucial for planets and life. But deeper still, magnetic storms unfold around neutron stars, especially magnetars, whose fields can reach 1,000 trillion times stronger than Earth's. These fields twist and contort the crust of the neutron star, releasing sudden bursts known as starquakes. In 2004, a magnetar in the constellation Sagittarius emitted a flare so powerful that it briefly affected Earth's upper atmosphere, despite lying over 50,000 light-years away. The physics behind these events arises from quantum interactions within ultra-dense matter, where neutrons form superfluid layers and magnetic pressure can fracture the surface. Storms also appear in the upper layers of gas giants. Jupiter's Great Red Spot, observed continuously since at least the 1,830 seconds, is a vast anticyclonic storm larger than Earth. Though far gentler in energy than supernovae or gamma-ray bursts, its persistence illustrates how atmospheric dynamics scale with size, rotation, and heat flow. Similar storms have been detected on exoplanets through high-resolution spectroscopy, showing winds exceeding thousands of kilometers per hour on hot Jupiters orbiting close to their stars. Cosmic storms can even emerge in the emptiness between galaxies. Shock waves, created by colliding galaxy clusters, heat intergalactic gas to tens of millions of degrees. Instruments such as the Chandra X-ray Observatory have mapped these turbulent regions, revealing vast arcs of hot plasma shaped by mergers that have taken billions of years to unfold. These cluster-scale storms provide insight into dark matter distribution, as gravitational influence shapes how gas moves and settles after collisions. On smaller scales, the solar wind generates storms that sweep across the solar system. This continuous stream of charged particles originates from the Sun's corona and interacts with planetary magnetic fields. The Earth's aurora is a gentle, visible trace of these interactions, recorded since ancient times and studied scientifically from the 17th century onward. More intense solar storms, driven by coronal mass ejections, can disrupt satellites and power grids, as demonstrated in the 1989 Quebec blackout. Their behavior reflects the Sun's magnetic cycles, which peak roughly every 11 years. Through all these examples, cosmic storms act as engines of change. They disperse elements, alter planetary atmospheres, sculpt star-forming regions, and reveal the violent interplay between gravity, magnetism, and radiation. The universe uses storms not only to dismantle structures, but also to create new ones, a balance observable across the smallest and largest scales. As these powerful outbursts ripple through space, they shape the environments from which quieter worlds emerge, guiding us toward places where sunlight fades, heat retreats, and the cosmos reveals landscapes preserved in deep and enduring cold. Frozen worlds. A dim glow on the horizon of interstellar space hints at the presence of frozen worlds, planets and moons locked in temperatures so low that chemistry slows, atmospheres collapse, and entire oceans turn to ice. These worlds dominate the outer reaches of planetary systems where weak starlight provides little warmth. In our own solar system, the Kuiper Belt and the distant Oort cloud contain countless icy bodies preserved since the earliest stages of planetary formation. Pluto, discovered in 1930 and later visited by the New Horizons mission in 2015, displays nitrogen glaciers, methane frost, and mountain ranges made of frozen water, evidence that even at 40 Kelvin, geological processes can persist. Beyond Pluto lies a realm where temperatures fall further still. Objects such as Eris, Makemake, and Sedna orbit in elongated paths that carry them into regions where sunlight is nearly absent. Their surfaces reflect the presence of volatile ices, methane, nitrogen, and carbon monoxide that sublimate during brief passages closer to the Sun, forming thin, temporary atmospheres before freezing again. Observations of these bodies through ground-based telescopes and the Hubble Space Telescope reveal variations in brightness caused by patches of reflective ice and dark organic compounds. Further inward, the icy moons of the gas giants hold some of the most intriguing frozen environments known. Europa, identified as an ocean world based on studies from the Galileo spacecraft in the 1990 seconds, contains a global subsurface sea kept liquid by tidal heating generated through its gravitational interaction with Jupiter. Venting plumes detected by the Hubble Space Telescope and later confirmed by reanalysis of Galileo data suggest water escapes through cracks in its ice shell. Enceladus, a moon of Saturn studied extensively by the Cassini mission, releases jets of water vapor and ice grains from its south pole. These plumes contain salts and organic molecules, pointing to hydrothermal activity beneath its frozen exterior. Even frozen exoplanets have begun to reveal themselves through precise measurements of starlight. Some orbit far beyond the habitable zones of their stars, receiving only enough energy to maintain surfaces colder than liquid nitrogen. Direct imaging has captured a few of these distant planets, showing faint infrared signatures from residual internal heat. Others may be rogue planets discussed earlier drifting without a star, their temperatures dictated solely by the slow release of primordial heat from their interiors. In such conditions, surface temperatures can reach tens of Kelvin, and any atmosphere would freeze into a thin, crystalline layer. The chemistry on these worlds evolves differently compared to warmer planets. At extremely low temperatures, molecular motion slows, and reactions take far longer to proceed. Ices become rigid, but can store complex organic molecules formed through interactions with cosmic rays and ultraviolet radiation. Studies of comets, such as the Rosetta mission's analysis of Comet 67P, Churyumov.Gerasimenko, show that these icy bodies preserve material older than the solar system itself. Their surfaces contain compounds like formaldehyde and simple amino acids, created in cold interstellar clouds and stored for billions of years until warmed by sunlight during perihelion. Frozen worlds also hold clues to planetary migration. The distribution of Kuiper belt objects suggests that giant planets shifted positions early in the solar system's history, scattering icy bodies outward. Simulations such as the NEAS model, developed in the early 2000s, reproduce this behavior and explain the presence of distant objects with irregular orbits. Though silent and motionless at first glance, frozen worlds remain dynamic on geological timescales. Their surfaces crack as internal heat escapes, their ices shift under seasonal changes, and their interiors may harbour oceans insulated from the vacuum of space. They demonstrate how varied planetary conditions can be, even within the same system. Endless night. A soft, starless hush stretches across vast stretches of interstellar space, giving form to the idea of an endless night, a cosmic environment where darkness is not merely the absence of light, but the natural state of most of the universe. The majority of space exists far beyond the reach of any star's warmth or illumination. Between galaxies, the density of matter drops to just a few atoms per cubic meter, leaving no medium for light to scatter and nothing for it to reflect from. The first hints of such emptiness appeared in early galaxy surveys of the 20th century, which revealed enormous voids spanning tens of millions of light-years. Regions so sparse that entire galactic clusters drift along their edges like islands bordering a silent sea. Yet within galaxies themselves, night remains the dominant backdrop. Even inside the Milky Way, where hundreds of billions of stars reside, most regions are too distant from any stellar neighbour to receive meaningful light. Darkness deepens inside molecular clouds, cold dense environments where dust grains absorb visible wavelengths and shield the interiors from starlight. These clouds, mapped extensively by infrared telescopes beginning in the 1980 seconds, reveal structures so opaque that even nearby stars disappear behind them, creating pockets of complete visual silence. However, as we shift our view toward cosmic time rather than cosmic space, the darkness becomes older still. After the Big Bang, the universe spent nearly 380,000 years as an opaque plasma. When it finally cooled enough for electrons and protons to form neutral hydrogen, light from that moment, the cosmic microwave background, began its long journey outward. But following this release, the universe entered an era known as the Cosmic Dark Ages. No stars yet existed, no galaxies had formed, and the only illumination came from faint interactions in cooling gas. This period lasted hundreds of millions of years, a stretch of true endless night in which structure slowly emerged under the influence of gravity. Once the first stars ignited massive, short-lived objects known as Population 3, stars, the darkness began to lift. Their radiation reionized the surrounding hydrogen, carving cavities of light into the gloom. Evidence of this process appears in deep sky surveys conducted with the Hubble and James Webb Space Telescopes, which detect early galaxies whose ultraviolet emissions mark the end of the cosmic dark ages. Yet, despite these luminous beginnings, darkness still dominates cosmic history. Stars flicker for millions or billions of years, but between their births and deaths, and between the galaxies that contain them, shadows stretch far wider. Night also takes on a particular character in the outer reaches of planetary systems. At distances where sunlight becomes faint, temperatures plummet. In the Oort cloud, nearly a light year from the sun, objects spend their entire existence in darkness. Their surfaces have been frozen for billions of years, revealing conditions similar to the cold interstellar medium. This region was first proposed by Jan Oort in 1950 to explain the long-period comets entering the inner solar system. Though no Oort cloud object has been directly observed, its gravitational influence remains consistent with models of comet distribution. For planets beyond the habitable zones of their stars, night may persist for geological ages with no interruption. Tidally locked worlds around red dwarfs, for instance, can have permanent night sides where starlight never reaches. Studies of such exoplanets using high-precision photometry and spectroscopy show large temperature gradients between hemispheres, shaping atmospheric circulation patterns and influencing potential habitability. Night becomes not only an absence of light but a fundamental driver of climate and chemistry. Endless night emerges as the dominant condition of the cosmos. Light arises only in rare, concentrated forms within stars, around black holes, and in short-lived bursts of energy. Everything else exists in gradients of shadow, from the deep voids between galaxies to the quiet interiors of unlit planetary systems. Darkness shapes the behavior of gas, the formation of stars, and the long-term cooling of the universe itself. Lost signals. A faint whisper crossing the void can travel for millions of years before arriving incomplete, illustrating the strange nature of lost signals messages from the universe that diminish, distort, or disappear entirely as they move through space. The earliest scientific attempts to detect such signals began in the 1930 seconds, with Carl Jansky's discovery of radio waves coming from the center of the Milky Way. His rotating antenna revealed that space was far from silent. It hummed with emissions from stars, gas clouds, and distant galaxies. Yet even then, much of what drifted toward Earth remained too weak or too scattered to interpret clearly. Far beyond the reach of ordinary starlight, radio waves carry information about environments obscured by dust. Pulsars, discovered in 1967 by Jocelyn Bell Burnell, emit steady pulses that travel across the galaxy with remarkable consistency. But interstellar plasma, electrons and ions distributed throughout the Milky Way slows and spreads these pulses, a process known as dispersion. By measuring this delay, astronomers can estimate how much matter lies between us and the source. In some cases, the distortion becomes so great that the original pattern nearly vanishes, leaving only faint traces of the signal's former clarity. Yet hidden within these scattered communications lie stranger phenomena. Fast radio bursts, first identified in 2007 from archived data collected by the Parkes Observatory, are millisecond flashes with energies comparable to a year's worth of solar output. Many originate from distant galaxies, billions of light-years away. Their signals arrive stretched and fragmented, shaped by every cloud, magnetic field, and plasma pocket they encounter. Though dozens of models have been proposed, the most supported explanations involve highly magnetized neutron stars capable of releasing enormous electromagnetic flares. As the bursts travel, they accumulate signatures from the cosmic web itself, offering clues about intergalactic matter too diffuse to observe directly. Lost signals also appear in optical and infrared observations, where the universe dims light through absorption and redshift. The expansion of the universe stretches wavelengths, causing distant galaxies to fade from visible sight. Edwin Hubble's work in the 1920 seconds revealed this relationship between distance and redshift, and later measurements, such as those from the Sloan Digital Sky Survey, mapped how countless galaxies drift toward invisibility as their light shifts into longer wavelengths. At extreme distances, light emitted when the universe was young becomes nearly undetectable, swallowed by the intervening gas that existed before reionization. Closer to home, spacecraft have contributed to the phenomenon of lost signals. The Pioneer and Voyager probes, now moving through the outer edges of the heliosphere, transmit data with power levels measured in mere watts. Their messages weaken as they disperse across billions of kilometers, requiring highly sensitive receivers on Earth to recover faint, noise-filled fragments. The Deep Space Network, created in the 1960 seconds, was designed specifically to detect these near-lost communications, demonstrating how carefully engineered equipment must be to follow a signal through the vast stretches of space. Even gravitational waves can experience a form of signal loss. Though not electromagnetic in nature, their amplitudes diminish with distance. The LIGO detections beginning in 2015 captured ripples from merging black holes more than 1 billion light-years away. Yet beyond certain ranges, these ripples fade below the threshold of detectability, leaving countless mergers unrecorded. The universe, it seems, produces signals at every scale, but only a fraction reach us with enough strength to reveal their origins. Lost signals remind us that the cosmos is filled with motion and communication, much of it fragile, much of it fading. They travel through darkness, shaped by gravity, gas, and expansion, carrying records of events long finished, empty space. A quiet stillness settles across the vast reaches between stars, revealing the true nature of empty space, an environment defined not by what exists within it, but by how little occupies its enormous volume. The idea that space could be nearly empty began taking scientific shape in the 19th century, but it wasn't until vacuum experiments and astronomical measurements advanced in the 20th century that the scale of this emptiness became clear. In regions far from galaxies, the density of matter drops to just a few atoms per cubic meter, so sparse that a cubic kilometer might contain fewer particles than a breath of Earth's air. However, empty space is never entirely empty. Even in its quietest expanses, the vacuum is threaded with electromagnetic fields, quantum fluctuations, and relic radiation from the early universe. The cosmic microwave background, the afterglow of the Big Bang, first detected in 1965 by Penzias and Wilson, fills all of space with a uniform bath of microwaves corresponding to a temperature of 2.7 Kelvin. This faint signal provides a record of conditions 380,000 years after the universe's beginning, preserved across 8 billion years of expansion, far beyond visible structures. The vacuum also contains what physicists call vacuum energy. According to quantum field theory, space cannot be entirely devoid of activity. Fields fluctuate even in their lowest energy states, producing virtual particles that appear and vanish too quickly to observe directly. Experiments like the Casimir effect, first predicted by Hendrik Casimir in 1948, demonstrate how boundaries placed in a vacuum can alter these fluctuations, creating measurable forces between uncharged metal plates. This phenomenon shows that empty space has physical properties, shaping how energy and matter behave at microscopic scales. Yet hidden within this emptiness lies the universe's largest framework, dark matter and dark energy. Dark matter, inferred through observations of galaxy rotation, curves in the 1,970 seconds, and later, through gravitational lensing studies, forms invisible halos around galaxies, guiding their structure and motion. Dark energy, discovered through supernova measurements in 1998, accelerates the expansion of the universe. Though neither has been directly detected, their influence is unmistakable. Much of the cosmos consists not of stars and planets, but of unseen components shaping everything from galaxy formation to the long-term fate of cosmic expansion. Still deeper into these remote regions, cosmic filaments stretch across intergalactic space, vast tendrils of dark matter and gas forming the scaffolding on which galaxies cluster. Mapping efforts such as the Sloan Digital Sky Survey reveal how these filaments define enormous voids, some over 300 million light-years across. Inside them, empty space dominates, presenting a landscape of near-perfect stillness. For photons travelling through this vacuum, paths are long and uninterrupted. For particles, motion is slow, collisions rare. Gravity acts across these distances, but even gravitational interactions weaken as matter becomes sparse. Despite its apparent simplicity, empty space influences the behavior of everything within the universe. Light traveling through vacuum experiences redshift as space expands, stretching wavelengths and making distant galaxies appear older and fainter. High-energy cosmic rays traverse these reaches, occasionally encountering background photons that alter their trajectories or energy. Even the propagation of gravitational waves, first directly detected in 2015, depends on the properties of space through which they travel, revealing subtle details about cosmic structure. Empty space, then, is less a void and more a stage, a vast, persistent backdrop shaped by quantum laws, gravitational architecture, and relic signals that predate galaxies themselves. It supports the transmission of light across billions of light-years, preserves ancient radiation, and sets the conditions under which matter clusters and evolves. These quiet expanses across the cosmos, structures begin to reappear, dim outlines shaped by gravity and light, forming regions where darkness gathers not from absence, but from dense, obscuring matter. These are the places where cosmic shadows take hold. Cosmic shadows. A faint dimming across a bright field of stars, often reveals the subtle presence of cosmic shadows, regions where light is absorbed, scattered, or warped by matter drifting silently through space. These shadows arise not from an absence of illumination, but from the intervening structures that block or distort radiant energy. The study of such shadows traces back to the early 20th century, when astronomers noticed dark lanes running through the Milky Way, features later understood to be dense clouds of interstellar dust. These clouds, composed of silicates, carbon grains, and ices, absorb visible light while allowing infrared wavelengths to pass, providing one of the earliest clues to the structure of the galaxy. Yet hidden within these dim regions are the stellar nurseries described in earlier segments, where gravity pulls gas into cold, dense concentrations. Observations with infrared and radio telescopes pioneered in the 1,950 seconds and 1,960 seconds revealed the internal architecture of these clouds. Within them, starlight cannot penetrate, creating pockets of near-total darkness. These shadowed areas hide protostars, forming behind thick curtains of dust. Without longer wavelength observations, these early stages of stellar evolution would remain invisible. But deeper still, cosmic shadows emerge on scales far larger than individual clouds. Galaxy clusters generate shadows through the Sunyaev-Zeldovich effect, discovered in the 1,970 seconds, where hot plasma interacts with cosmic microwave background photons, slightly boosting their energy and imprinting subtle features on the background radiation. These imprints reveal the distribution of matter across clusters, helping astronomers map large-scale cosmic structures. On even grander scales, gravitational lensing creates shadows of a different kind. Massive objects such as galaxies and clusters bend the path of light from sources behind them. In some cases, this bending focuses light into arcs or multiple images. In others, it creates weak distortions, so subtle that only statistical analyses reveal them. These distortions, known as weak lensing, allow astronomers to infer the presence of dark matter, giving shape to the invisible halos surrounding galaxies. Surveys like the Dark Energy Survey and Euclid mission specialize in mapping these shadows cast by gravity itself. Cosmic shadows also appear in exoplanet research. When a planet transits its star, it casts a minute shadow detectable through changes in the star's brightness. The transit method, first successful in the 1,990 seconds and refined through missions like Kepler and TESS, allows astronomers to measure planetary sizes, orbital periods, and even atmospheric composition. Tiny variations in the depth and timing of these shadows reveal additional planets, moons, or rings. Even in planetary systems far beyond our own, shadows provide critical insight into structures too small and faint to observe directly. Closer to home, shadows arise in the outer solar system, where sunlight grows thin. Comets approaching the Sun exhibit dust tails that cast faint shadows across their surrounding coma. The Rosetta spacecraft's detailed study of Comet 67P showed how surface geometry and dust outflow create shifting patterns of light and dark across the nucleus. These patterns, recorded in high resolution, reveal how icy surfaces evolve as they warm and release gas into space. Despite the wide range of phenomena that create them, cosmic shadows share a unifying feature. They reveal the presence of something that cannot be seen directly. Through absorption, distortion, or interruption, shadows mark where matter gathers, where light struggles, and where gravity shapes the path of energy across the universe. Wandering suns. A lone glow drifting through the dark reveals the quiet motion of wandering suns' stars that travel the galaxy without remaining tied to any stable neighborhood. though most stars orbit the Milky Way in orderly paths, a surprising number move along trajectories that set them apart, propelled by gravitational encounters, stellar explosions, or the dynamic evolution of the galactic disk. Their existence was confirmed through proper motion studies, beginning in the early 20th century, when astronomers like Ejnar Hertzsprung and Willem de Sitter noticed stars shifting noticeably against the background sky. Later, surveys such as Hipparcos and Gaia refined these measurements, mapping the motions of more than 1 billion stars and revealing how many wander far from their birthplaces. Some wandering suns originate from densely packed star clusters. In these environments, gravitational encounters act like celestial billiard shots, sending stars careening outward at high speeds. Open clusters gradually lose members over hundreds of millions of years, their stars dispersing into the galactic field. Globular clusters, though far older and more tightly bound, also eject stars through close interactions with binary systems or black holes at their centers. These ejected stars, known as runaway stars, can reach velocities of hundreds of kilometers per second. Their paths arc across the galaxy, carrying them into regions where star formation is rare and interstellar matter is thin. Yet, hidden within these drifting populations lies an even stranger class: hypervelocity stars. First identified in 2005, these stars move so quickly, several million kilometers per hour, that they are destined to leave the Milky Way entirely. Their extraordinary speeds arise from interactions with the supermassive black hole at the galactic center. When a binary star approaches too closely, tidal forces can tear the pair apart, capturing one star while ejecting the other with enormous energy. These stars travel on long, graceful trajectories into intergalactic space, becoming isolated suns wandering the void for billions of years. However, as we shift our view to slower forms of stellar drift, another story emerges. The Milky Way's structure is not fixed. Its spiral arms, bar, and halo move and evolve over time. Interactions with dwarf galaxies, such as the Sagittarius dwarf spheroidal galaxy, currently merging with the Milky Way, stir the stellar population, creating streams of stars that once belonged to different systems. These stellar streams, mapped through Gaia data, trace the galaxy's gravitational history, showing how stars migrate outward, inward, or across the disk in vast waves shaped by dark matter and tidal forces. Some wandering suns are relics of ancient populations. Halo stars, among the oldest in the galaxy, orbit in large, elongated paths well above and below the galactic plane. Their chemical compositions contain fewer heavy elements, indicating that they formed when the universe was still young and lacked the enriched material produced by multiple generations of supernovae. Their motion through the disk occurs only occasionally, and when they pass through, they do so with immense velocity, barely influenced by the gas and dust that slow younger stars. Despite their solitude, wandering suns contribute significantly to the galaxy's evolution. Their motion stirs interstellar gas, influences the distribution of heavy elements, and shapes star-forming regions over long timescales. When a wandering star passes close to a planetary system, its gravity can disrupt comet reservoirs or shift orbital alignments, though such encounters are rare on human timescales. Over billions of years, however, these interactions accumulate, subtly steering the architecture of galactic systems. Wandering suns remind us that even stars, seemingly anchored in place, drift through the galaxy in quiet arcs, shaped by gravity's slow and persistent influence. They carry the memory of their origins, the scars of interactions, and the momentum of distant encounters. Invisible forces, a gentle distortion of motion, detectable only through the behavior of stars and galaxies, hints at the presence of invisible forces phenomena that shape the universe despite leaving no direct trace we can observe with light. The most familiar among these is gravity itself, long recognized but only fully understood in the early 20th century through Einstein's general theory of relativity. According to this model, gravity is not a force in the traditional sense, but the curvature of space-time shaped by mass and energy. Light bends around massive objects, time slows under strong gravitational fields, and objects follow paths determined by this geometry. The first empirical confirmation came in 1919 when Arthur Eddington observed starlight bending around the Sun during a solar eclipse, matching Einstein's predictions. Yet hidden within the structure of galaxies lies evidence of a second, more mysterious influence. In the 1,970 seconds, astronomer Vera Rubin measured rotation curves of spiral galaxies and found that stars in the outer regions moved far faster than expected based on visible matter alone. To account for this discrepancy, scientists proposed the existence of dark matter, a form of mass that interacts gravitationally but does not emit, absorb, or reflect light. Dark matter is thought to form large halos around galaxies, extending well beyond their visible edges and providing the additional gravity necessary to maintain their high rotation speeds. Observations of gravitational lensing, particularly in systems like the Bullet Cluster, reinforce this idea by showing how mass can shift independently of luminous material. However, the universe contains another invisible influence: dark energy. Its existence was revealed in 1998 through studies of type Ia supernovae, which demonstrated that the expansion of the universe is accelerating. This acceleration cannot be explained by gravity alone, and instead suggests the presence of a form of energy permeating space that counteracts gravitational attraction on large scales. Dark energy constitutes roughly 68% of the total energy content of the universe, shaping its long-term evolution and determining its ultimate fate. On smaller scales, invisible forces also arise through electromagnetic fields. Though electromagnetic radiation is visible in certain forms, the fields themselves permeate space even without producing light. The interstellar medium contains tangled magnetic fields measured through the polarization of starlight and the behavior of cosmic rays. These fields influence star formation, guide charged particles, and shape the structure of interstellar gas. Even the heliosphere, the bubble carved by the solar wind around the solar system, is shaped by magnetic interactions between solar plasma and the surrounding interstellar environment. Quantum mechanics introduces yet another layer of invisible influence. Quantum fields, which describe every particle in the universe, fluctuate constantly. These fluctuations produce forces such as the Casimir effect and contribute to phenomena like Hawking radiation near black holes. Although these interactions occur on scales far smaller than atoms, they influence processes across physics, from nuclear stability to the formation of chemical bonds. Invisible forces not only shape matter, but also reveal themselves through the patterns they leave behind. Galaxy surveys show how dark matter arranges cosmic filaments, while observations of the cosmic microwave background trace subtle temperature variations caused by density differences in the early universe. Precision measurements of pulsars indicate how gravitational waves ripple through space-time, a discovery first confirmed directly in 2015 by the LIGO observatories. These influences, though unseen, govern how the cosmos evolves. They guide the motion of wandering suns, shape the growth of galaxies, and determine how space stretches across billions of light years. Invisible forces act as the underlying framework of the universe, quiet, persistent, and essential. These hidden structures orchestrate the grand motion of cosmic systems. Attention turns toward the boundaries of time itself, where the slow aging of stars and galaxies reveals the faint glow of the universe's earliest moments and the lasting echo of its first light. Time stretching. A soft distortion in the rhythm of events reveals the quiet phenomenon of time stretching, a consequence of relativity where time itself flows at different rates depending on gravity and motion. This principle, woven into the fabric of Einstein's theories in the early 20th century, changed not only physics, but our understanding of what time actually is. Rather than a universal clock beating uniformly across the cosmos, time becomes a local experience, flexible, elastic, and deeply dependent on the conditions surrounding it. The stronger the gravity or the faster the motion, the more dramatically time stretches. The roots of this idea emerged in Einstein's 1905 paper on special relativity. He demonstrated that objects moving close to the speed of light experience time differently from objects at rest. This wasn't a philosophical musing, it was a mathematical consequence of insisting that the speed of light remains constant to all observers. Experiments decades later confirmed this behavior. High-energy muons created in Earth's upper atmosphere, which decay in millionths of a second, were found to survive far longer when travelling at relativistic speeds in particle accelerators. Their internal clocks slowed compared to ours, allowing them to reach detectors they would never reach otherwise. However, as we shift our view from speed to gravity, an even richer picture emerges. General relativity, published in 1915, reframed gravity not as a force, but as the curvature of space-time created by mass. The deeper an object sits in a gravitational well, the slower time passes for it. This was first demonstrated experimentally in 1959 through the Pound-Rebka experiment, which measured gravitational redshift, the slight lowering of photon frequency as light climbed out of Earth's gravitational well. Further confirmation came with Gravity Probe A in 1976, which launched a precise atomic clock aboard a sounding rocket. As the rocket reached higher altitudes and weaker gravity, the onboard clock ran faster relative to its counterpart on Earth. The difference, tiny but measurable, matched theoretical predictions exactly. Since then, numerous satellite-based experiments have further refined our understanding, and today, even everyday systems rely on these effects. The Global Positioning System provides a perfect illustration of time stretching in action. GPS satellites orbit Earth in regions where gravity is weaker and where their orbital speed is high. Both conditions alter their internal clocks. If left uncorrected, these discrepancies would cause GPS calculations to drift, accumulating errors of several kilometers per day. Instead, engineers program satellites to run slightly slower so that, when relativistic effects are accounted for, the clocks match Earth-based reference time. Time stretching, therefore, is not an abstract idea, it is embedded in our technology. Near massive bodies, however, these effects multiply dramatically. A neutron star, only about 20 kilometers wide, yet containing more mass than the Sun, generates a gravitational field so intense that time on its surface passes measurably slower than in surrounding space. Photons climbing out of this gravitational well lose energy, shifting their wavelengths toward the red end of the spectrum. Observations of neutron star spectra confirm this effect, revealing gravity's direct imprint on light. But deeper still lies the physics of black holes objects whose gravitational pull is so strong that time stretching becomes extreme. For a distant observer, anything falling toward a black hole appears to slow, dim, and redden as it approaches the event horizon. The falling object's signals take longer to escape, their wavelengths become stretched, and eventually they fade completely. To the outside universe, the object never quite crosses the horizon. It simply dissolves into deeper red until its light disappears. Yet from the perspective of the falling object itself, time feels perfectly normal. It crosses the event horizon in finite time, experiencing no sudden shift. This extraordinary contrast reveals a fundamental truth. Time stretching is always relative. Different observers are not merely seeing the same events from different angles, they are experiencing reality at different rates. On cosmic scales, the universe displays time stretching in yet another form, the stretching of light due to cosmic expansion. Light from distant galaxies becomes redshifted as space itself expands during its journey to us. A supernova in a galaxy billions of light years away will appear to unfold more slowly than an identical explosion in a nearby galaxy. Its rise and decline in brightness are stretched by the expansion of the universe. Observations of high redshift supernovae using the Hubble Space Telescope have provided clear examples of this effect, forming part of the evidence for dark energy, the mysterious influence accelerating cosmic expansion. Time stretching also plays a role in the early universe. During the inflationary period, fractions of a second determined the distribution of matter across cosmic scales. Density fluctuations stretched with expanding space, giving rise to the subtle variations we now detect in the cosmic microwave background. Missions like COBE, WMAP, and Planck mapped these variations with astonishing precision, revealing how the earliest processes were governed by intense, rapid shifts in time and space. Through all these contexts, time stretching emerges as a quiet sculptor of cosmic experience. It influences everything from the decay of particles to the behavior of light, from the clocks in our satellites to the structure of the universe itself. Time, once thought fixed and universal, reveals itself as a dynamic property shaped by gravity, motion, and expansion. Final light. A dwindling radiance lingering in the depths of space marks the quiet phenomenon of final light, the last glow emitted by stars as they approach the end of their nuclear lifetimes. For billions of years, stars fuse hydrogen into helium in their cores, maintaining a delicate balance between gravitational collapse and outward pressure. But this equilibrium is temporary. Eventually, their fuel runs low, and the light that once sustained planets, shaped nebulae, and illuminated cosmic landscapes begins to fade. For sun-like stars, this decline unfolds gently. These stars expand into red giants, swelling as their cores contract and heat up. The helium ash from hydrogen fusion becomes the new fuel source, igniting in what is known as the helium flash, an explosive but internal event first understood through stellar modelling in the mid-20th century. Their outer layers drift outward over hundreds of thousands of years, forming planetary nebulae, vast, colourful shells captured in images by telescopes like Hubble. These nebulae glow briefly, illuminated by ultraviolet radiation from the star's exposed core, before dispersing into surrounding space. What remains behind is a white dwarf, a dense, Earth-sized remnant with the mass of a star packed into a crystalline lattice of ions, supported by electron degeneracy pressure. White dwarfs no longer produce energy through fusion. They shine only from residual heat. Cooling curves developed since the 1950 seconds show how this fading proceeds over billions of years. Eventually, long after the current age of the universe, white dwarfs would cool enough to become black dwarfs, frozen, lightless remnants. None yet exist. The universe is simply not old enough for any star to have cooled that far. But deeper still lies the final light of massive stars. When such stars exhaust their nuclear fuel, their cores collapse in milliseconds. The implosion triggers a supernova explosion so powerful that it can briefly outshine an entire galaxy. Records of these events appear throughout history. The 1054 supernova that formed the Crab Nebula, the 1604 supernova observed by Kepler, and more recent examples seen with the aid of modern instruments. These spectacular bursts seed the cosmos with heavy elements, iron, gold, uranium, and others formed in the extreme conditions of collapse. For the surviving core, the end depends on its mass. If the core remains below about 2.5 solar masses, it becomes a neutron star, a dense object held up not by electrons, but by neutron degeneracy pressure. Neutron stars emit beams of radiation as they rotate, producing pulsars. These pulses, discovered in 1967, fade as rotational energy drains away, offering a slow, rhythmic form of final light. Magnetars, with magnetic fields trillions of times stronger than Earth's, release bursts of X-rays and gamma rays as their crusts crack, their energy output declining gradually over thousands to millions of years. But if a massive star's core surpasses the neutron limit, gravity wins completely, forming a black hole. Though black holes themselves emit no light, their surroundings may shine brilliantly. Gas spiraling inward forms an accretion disk, heating to millions of degrees. The final light of such a system comes not from the black hole, but from the dying matter orbiting it. Final light also carries a cosmological meaning. As the universe expands, starlight stretches into longer wavelengths. Over trillions of years, most stars will exhaust their fuel, leaving only faint remnants. Galaxies will drift so far apart that their light will no longer reach one another. The cosmic microwave background, already cooled to 2.7 Kelvin, will stretch into wavelengths too long to detect. Light itself becomes sparse, then rare, then distant. In this slow dimming, the cosmos moves toward a dark, diffuse future, governed by cold remnants and long-decayed energy sources. Final light is not a sudden extinguishing. It is a quiet, gradual retreat of illumination in a universe governed by thermodynamics and expansion. As this gentle glow fades into deeper shadow, the structures that remain neutron stars, white dwarfs, wandering planets, continue their slow evolution, carrying forward the last echoes of the stars that once shaped the cosmic landscape. Quiet collisions. A faint ripple moving through the darkness reveals the gentle power of quiet collisions, events where cosmic structures meet not with explosive force, but with slow, deliberate motion shaped by gravity and time. Unlike the abrupt images one might associate with collisions on Earth, most encounters in the universe unfold over millions or even billions of years. Stars pass near one another without touching. Galaxies merge through elegant spirals, and clouds of gas drift together in motions so gradual that their energy manifests not as violent detonations, but as soft rearrangements of matter. These interactions are governed by gravitational dynamics, first described in detail through Newton's work in the 17th century, and later refined through modern astrophysics, revealing a cosmos where even collisions possess a calm, almost meditative character. Far beyond the solar system, the Milky Way itself is shaped by these slow gatherings. Our galaxy is currently interacting with the Sagittarius dwarf spheroidal galaxy, a smaller companion that orbits and gradually disintegrates under the Milky Way's gravity. This process, mapped in exquisite detail using data from the Gaia spacecraft, forms long streams of stars stretched across the galactic halo. These stellar streams, do not tear through space with dramatic force, but drift quietly, tracing the history of past encounters like the fading imprint of a cosmic tide. Yet hidden within this grand choreography, star clusters offer a more intimate view of quiet collisions. In open clusters, where young stars form together from the same cloud of gas, stellar encounters are common but gentle. Gravity subtly alters their orbits until the cluster loosens over hundreds of millions of years. Globular clusters, far denser and older, show a different pattern. Here, stars occasionally pass close enough for gravitational slingshots to occur, sending one star outward at high speed while another settles deeper into the cluster. These events rarely involve physical contact. Stars are so far apart relative to their size that even in the densest environments, direct collisions remain extremely rare. Yet gravitational exchanges slowly restructure entire clusters, shifting their mass distributions and influencing their long-term evolution. However, as we shift our view outward to interstellar gas, collisions take a different form. Giant molecular clouds, vast cold reservoirs of hydrogen, drift through the galaxy and occasionally merge. Their meeting compresses the gas, triggering star formation. Observations of regions like the Orion Nebula show how these interactions drive turbulence, density waves, and ultimately gravitational collapse. The resulting stars, though brilliant, are born from processes that began with remarkably soft encounters, drifting clouds merging over millions of years. On galactic scales, quiet collisions become even more striking. When galaxies meet, they do not crash like solid objects. Instead, their stars pass largely unharmed, while their gas, dust, and dark matter interact through gravity and friction-like processes. The merger between the Milky Way and the Andromeda Galaxy, predicted to occur in roughly 4 billion years, will be a prime example. Simulations show that individual stars will mostly avoid direct contact, yet the galaxies will reshape one another through tidal forces, forming long tails and streams. Eventually, after billions of years, the two will settle into a single, larger galaxy. Galactic collisions also stimulate star formation. When gas clouds within colliding galaxies meet, they slow down, compress, and ignite bursts of new stars. Observations of interacting systems, like the antennae galaxies, reveal dense knots of star formation triggered by these gentle compressions. Even the dramatic arcs and tails of these galaxies result not from explosive encounters, but from the graceful stretching of material along gravitational pathways. Quiet collisions influence the structure of the universe on every scale. Dark matter, though invisible, contributes to these interactions by shaping gravitational potentials. Galaxy clusters form through mergers of smaller structures, guided by dark matter halos that grow through accumulation. The bullet cluster, observed through X-ray and gravitational lensing studies, offers a particularly clear example. The ordinary matter, slowed by collision, lingers at the center, while the dark matter, unaffected by such interactions, passes through relatively undisturbed. Within these vast spaces, even the faintest collisions echo across time. Dust grains, drifting through the interstellar medium, occasionally meet and stick together through electrostatic forces, beginning the slow process of forming larger particles, then rocks, then planets. Every world that exists today, Earth included, originated from trillions of such microscopic encounters, each quiet and unremarkable on its own, yet transformative in aggregate. In this way, quiet collisions act as the universe's patient architects, shaping galaxies, nurturing star formation, and building the foundations of planets. They remind us that cosmic change often emerges not from violence, but from steady, persistent interactions. Edge of nothing. A delicate thinning of starlight across the horizon of space reveals the elusive boundary known as the edge of nothing. Regions where matter grows scarce, energy fades, and the structure of the universe begins to dissolve into near emptiness. This concept does not mark a physical edge, for the universe has no walls, but represents the point at which cosmic density becomes so low that familiar processes no longer operate in recognizable ways. It is a frontier defined not by the presence of something, but by the profound absence of almost everything. The large-scale structure of the universe, mapped through projects such as the Sloan Digital Sky Survey, reveals a vast web of galaxies, threaded into filaments separated by enormous voids. These voids, spanning hundreds of millions of light years, contain only a few atoms per cubic meter, far less than the interstellar medium within galaxies. Within these expanses, galaxies drift faintly, isolated from one another by immense distances. Time behaves normally here, yet the processes that shape dense cosmic regions slow dramatically. Star formation ceases, interactions diminish, and the universe enters a quieter state. Far beyond the familiar presence of galactic filaments, dark energy influences these regions most clearly. Discovered through observations of type Ia supernovae in 1998, dark energy drives the accelerated expansion of the universe. Where matter is already sparse, this expansion becomes most pronounced. Over billions of years, galaxies in these voids drift further apart, their light stretched into longer wavelengths until it becomes nearly impossible to detect. In these realms, the edge of nothing feels not like a boundary, but like a thinning, an ongoing, gentle unraveling of cosmic structure. Yet hidden within this larger emptiness, even the smallest traces of matter hold significance. A lone hydrogen atom drifting through intergalactic space may not seem remarkable, but its movement traces gravitational potentials shaped by dark matter halos extending far beyond galaxies. Observations of gravitational lensing reveal these invisible structures, showing how they bend light from distant quasars and galaxies. Even in near emptiness, the universe maintains a hidden framework. However, as we shift our view to the most remote objects observed, the edge of nothing takes on a historical dimension. Light from the earliest galaxies, captured by telescopes such as James Webb, reveals systems forming only a few 100 million years after the Big Bang. Their faint illumination has travelled for more than 13 billion years, stretched by cosmic expansion into infrared wavelengths. Beyond this lies the cosmic microwave background, the faint afterglow of the early universe detected by Arno Penzias and Robert Wilson in 1965. It represents the oldest light we can observe, marking a boundary not of space but of time, a horizon beyond which the universe was opaque. In the far future, the edge of nothing becomes more literal. As expansion continues, galaxies outside the local group will move beyond our observable horizon. Their light, stretched endlessly, will no longer reach us. Over trillions of years, even the faint afterglow of the cosmic microwave background will shift beyond detectability. The universe becomes increasingly dark, cold, and diffuse. Final stars fade into white dwarfs, then black dwarfs. Neutron stars cool. Black holes evaporate through Hawking radiation calculated in 1974. The cosmos approaches a state of near emptiness governed by weak interactions and residual quantum fluctuations. This gradual journey toward nothingness is driven not by sudden collapse, but by slow, persistent expansion. Thermodynamics plays a central role. As energy spreads thin, entropy increases, and the universe trends toward equilibrium, a state where no large-scale structures remain to create new complexity. In this distant era, even occasional interactions between particles become rare. The universe enters a long twilight, where time stretches endlessly against the backdrop of thinning matter. The edge of nothing, therefore, is both a physical region and a conceptual direction. It marks the transition from structure to emptiness, from galaxies to voids, from light to darkness. Yet, it is not a sharp threshold. It is a gradient, a soft tapering of cosmic presence that invites contemplation of the universe's long-term evolution. This frontier expands. It gently guides us toward the remaining chapters of cosmic history regions, shaped by the faintest traces of matter and the near-silent interactions that persist even when the universe stands on the threshold between presence, absence. Strange signals. A faint pulse drifting through the vastness reveals the quiet mystery of strange signals, brief flashes of energy that arrive from deep space with patterns that defy simple explanation. These signals, detected through radio telescopes since the mid-23rd century, often originate from regions far beyond our galaxy, carrying information about extreme cosmic environments. Their discovery began modestly in 1967, when Jocelyn Bell Burnell identified a series of precise, rhythmic pulses while studying distant radio sources. At first, their regularity seemed so unnatural that the research team jokingly labelled them LGM-1, short for Little Green Men. Eventually, these pulses were recognized as emissions from rapidly rotating neutron stars, pulsars. But the moment marked the beginning of an era in which the cosmos began to speak in unfamiliar signals. Far beyond the steady ticking of pulsars, newer and far stranger patterns have emerged. Fast radio bursts, or FRBs, were first confirmed in 2007 through archived data from the Parkes Observatory. These bursts last mere milliseconds yet release as much energy as the Sun emits in days. Some repeat at irregular intervals, others flare once and never return. Despite efforts to understand their cause, no single explanation applies to all of them. Observations from the CHIME telescope in Canada have catalogued hundreds, revealing some sources with periodic patterns and others with chaotic timing. The variety hints at multiple origins. Magnetars undergoing starquakes, collisions of compact objects, or interactions in dense plasma environments. Yet hidden within these bursts are even more enigmatic features. Certain FRBs exhibit complex frequency structures, with signals that sweep downward in tone as they arrive an effect called dispersion, caused by intergalactic electrons slowing higher frequencies less than lower ones. This dispersion provides a rough measure of a signal's distance, indicating that many FRBs originate from billions of light-years away. Their extreme energy suggests processes occurring in highly magnetized regions, possibly near young magnetars formed in powerful supernovae. In 2020, an FRB-like burst was detected from within our own galaxy, linked to the magnetar SGR 1935 plus 2154, giving crucial insight into how at least some bursts form. However, as we shift our view to other unusual signals, the puzzle grows. Quasars' bright, energetic cores of distant galaxies powered by supermassive black holes emit radio and optical signals that vary across timescales ranging from hours to months. Their brightness fluctuations help astronomers probe the size and structure of accretion disks, though the irregular patterns often challenge modelling efforts. Meanwhile, gamma-ray bursts, the brightest electromagnetic explosions in the universe, produce high-energy flashes that can trigger alerts on orbiting observatories like Swift and Fermi. Some bursts last less than 2 seconds, others extend beyond a minute. Their origins range from merging neutron stars to the collapse of massive stars into black holes. Another category of strange signal comes from repeating, perfectly timed pulses produced by millisecond pulsars. These objects rotate hundreds of times per second with remarkable stability, making them natural cosmic clocks. Networks of these pulsars form pulsar timing arrays, which measure tiny deviations in pulse arrival times caused by gravitational waves stretching and squeezing spacetime. In 2023, several collaborations, including Nanograv and the European Pulsar Timing Array, reported evidence of a gravitational wave background generated by merging supermassive black holes across the universe. These signals are not bursts or flashes, but a subtle tremor woven into the timing of pulsars themselves. Even more mysterious are signals that appear once and never return. The most famous among them, the WOW signal, detected in 1977 by the Big Ear radio telescope, lasted 72 seconds and bore no obvious natural explanation at the time. Despite extensive efforts, no repeat has ever been observed. Most astronomers now suspect a natural origin, possibly a narrowband emission from a distant comet or a transient cosmic event, but the lack of conclusive evidence keeps it in scientific memory as an intriguing anomaly rather than a confirmed phenomenon. Signals also emerge from the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature variations in this radiation were mapped in detail by missions such as COBE, WMAP, and Planck, revealing subtle irregularities that trace the early universe's density fluctuations. These slight variations are not signals in the traditional sense, but patterns encoded in radiation that has travelled for 13.8 billion years, carrying information about the universe's infancy. Strange signals demonstrate that the cosmos communicates not in words, but in shifts of energy, bursts of radiation, and patterns of timing that reflect conditions in distant, extreme environments. They remind us that the universe remains filled with processes we cannot fully predict or categorize. Each detection deepens our understanding of astrophysics while leaving room for wonder, challenging us to refine our instruments, re-evaluate our assumptions, and look more deeply into the dark. As these mysterious transmissions continue to arrive from across the sky, they form a quiet thread connecting us to regions where gravity, magnetism, and energy behave in unfamiliar ways, guiding us naturally toward the next unseen frontier, shaped by forces beyond ordinary perception. Cosmic giants. A faint glow, spreading across the largest structures in the universe, reveals the presence of cosmic giants, titanic assemblies of galaxies, gas, and dark matter that shape the architecture of the cosmos. These giants appear in many forms: galaxy clusters, superclusters, and the filaments of the cosmic web mapped through deep surveys. They represent the largest gravitationally bound structures known, each tracing the influence of dark matter halos formed in the universe's early stages. Galaxy clusters sit at the heart of this hierarchy. Containing hundreds to thousands of galaxies bound together by gravity, they are permeated by hot intracluster gas that emits X-rays detectable by telescopes such as Chandra and XMM Newton. The first hints of these clusters emerged in the early 20th century when astronomers like Fritz Zwicky observed galaxies in the Coma cluster moving far faster than expected. He proposed the existence of unseen mass, what we now call dark matter, to explain the discrepancy. Later observations confirmed that dark matter outweighs visible matter in clusters by a factor of about 5. Yet hidden within these clusters are even more massive structures, the brightest cluster galaxies, often located near the center. These galaxies grow by absorbing smaller companions through mergers that unfold over billions of years. Their size and luminosity make them landmarks within the cluster environment, anchoring the gravitational potential around which other galaxies orbit. But deeper still lies the structure of superclusters, vast groupings of clusters and galaxy groups, stretching across hundreds of millions of light-years. Our own Milky Way belongs to the Laniakea supercluster, mapped in 2014 by studying the motion of galaxies within a gravitational basin. Laniakea extends across 500 million light-years and contains roughly 100,000 galaxies. Its structure flows along filaments that converge near massive clusters like the Norma cluster, forming a gravitational landscape with valleys and ridges determined largely by dark matter. However, as we shift our view outward from these giants, an even grander pattern becomes clear. The cosmic web, revealed through large surveys such as the Sloan Digital Sky Survey and simulations like Illustris TNG, shows how matter distributes itself in interconnected filaments, sheets, and nodes. Between these filaments lie enormous voids, regions almost entirely empty. The formation of this web began shortly after the Big Bang, driven by density fluctuations recorded in the cosmic microwave background and amplified by the gravitational pull of dark matter. In these filaments, galaxies grow by accreting gas and merging with others. Galaxy clusters draw material from multiple directions, feeding their expansion. Observations of the Virgo cluster, the Coma cluster, and the Perseus cluster show how gas flows inward along these filaments, heating as it compresses and emitting X-rays detectable across millions of light-years. Cosmic giants also produce some of the most energetic phenomena known. Colliding galaxy clusters generate shockwaves in their intra-cluster gas, visible in radio wavelengths through synchrotron emission. The Bullet cluster, one of the most studied examples, provided clear evidence for dark matter by showing how ordinary matter slowed during collision, while invisible mass passed through relatively unaffected. These interactions reshape clusters over time, merging structures into even larger giants. On still vaster scales, simulations predict that cosmic giants will continue to grow as long as galaxies remain close enough to be gravitationally attracted. However, dark energy driving the accelerated expansion of the universe will eventually limit their growth. Over billions of years, only structures already gravitationally bound, such as galaxy clusters, will remain intact. Superclusters not fully bound will drift apart, and the cosmic web will slowly thin as expansion increases. These giants serve as the framework upon which the universe's history is built. Their size reveals how matter organizes itself under gravity. Their behavior highlights the influence of dark matter and dark energy. Their evolution tells the story of cosmic time on the largest scales.